Hello everyone. So today's session will be discussing about once again the same flip-flops as we discussed in the previous session. We started with the previous session, what is a flip-flop and what is a latch. We discussed the difference between the latch and a flip-flop. So now we are going to still extend the operation of all these flip-flops, different types of flip-flops with respect to edge triggering. Also we discussed in the previous section about the edge triggering and level triggering. So with respect to that, in view of that, we'll discuss in depth about the edge triggering flip-flops. It could be RS, D and JK. We'll discuss the flip-flop JK, how the JK flip-flop works. We'll discuss the timing problem related to these flip-flops, and there is another concept called contact bounce. So we'll state the cause of this contact bounce and describe the solution for how to come out of this contact bounce problem. Then we'll be learning characteristic equations, how to represent or how to write a characteristic expression for flip-flops. As well, we'll discuss the excitation table of flip-flops. So let me start with edge triggered RS flip-flop. As we discussed in the previous session, there is a difference between edge triggering and level triggering. So when I talk about edge triggering, so I always consider this as either the rising edge or falling edge of the clock. As you know well, what is a clock? Clock is nothing but continuous train of pulses. So this clock is represented as 0 to 1 transition and 1 to 0 transition back. So this transition we treat from moving from 0 to 1 transition, that edge is called as rising edge, positive edge. Similarly, the triggering from 1 to 0, that edge is treated as falling edge or negative edge. So this is what we discussed in the previous session. So you can see the block diagram of flip-flop, SR flip-flop. So with this arrow represents positive edge triggering. So whenever I represent arrow over here, it represents positive triggering. If I represent an arrow with a bubble over here, it represents a negative edge triggering. So this is the symbol of SR edge triggered flip-flop. So we'll discuss now the operation of edge triggered RS flip-flop. As usual, we have SR inputs, set and reset inputs. We discussed using NAND gate as well as NOR gate latch. So now we are discussing the same SR flip-flop along with the clock. This SR has got two inputs. This flip-flop has two inputs, S and R, wherein I represent these two inputs as 4 combinations. You can just see over here there are 4 combinations. So this C represents clock. Arrow upwards represents it as positive edge triggered flip-flop. So now I am writing this truth table for this. The outputs are Q and Q complement. Since I know in case of SR flip-flop, when both the inputs are 0, there is a no change condition. So whatever the previous state, that remains as it is. So we call this as no change condition. Similarly, when I give input to S as 0 and R as 1, when my clock is I, my output is in reset condition. So when my output is 0, we call this condition as reset condition. So similarly, when I give S is 1, R 0, when clock is I, my output remains in set condition. So similarly, if I give 1-1 combination for these S and R inputs, so then it is an invalid indeterminate condition as we discussed in the previous session. So this is the representation of edge triggered RS flip-flop with the inputs as well as a clock positive triggering, where I will be giving 0 to 1 transition clock, and this flip-flop will respond with respect to this transition. You can see the timing diagram over here. In the timing diagram, we will be checking all combinations of S and R. So S and R with respect to clock. So clock is nothing but train of pulses. You can see here one clock cycle represents a transition from high to low. This represents one clock transition, and once again the second as it is continuous. So this is a clock. The first signal that is coming in this timing diagram is nothing but clock. So next is S and R. So let us discuss now the various combination over here. So whenever there is S is 1 here, you can see I am representing this vertical line. Vertical line indicates it's an edge. So this represents edge of this first clock transition. This is the second clock transition edge. Similarly, I write for all edges vertical line. So this represents edge. With respect to edge, whatever the inputs are given, output will be reflected. So as you see at this particular edge, first clock transition, you can see S is high and R is low. So when S is high and R is low, according to my truth table as we discussed previous, my output goes to set condition, true. So my output is now in set condition, that is nothing but logic 1. So Q remains logic 1 till where? Yeah, it is till the next transition starts, even though you can just see here in between S has come to low, R has come to high, but my output remains same as previous. This infers whenever I give the inputs at the edge, whatever the inputs are there at the edge, then only the same output is reflected until the next edge triggers. So when the next edge is triggered, you have to see the inputs at that moment. And now the inputs are that moment, S is R, S is 0 and R is 1. So this is nothing but reset condition. My output now switches back to 0. From logic 1 to logic 0. So this output logic 1 is in set condition, here it is in reset condition. It remains until same for the next edge. So when the next edge comes, you have to see the inputs of S and R. Now the inputs of S and R both 0 0. 0 0 means according to our truth table, SR flip flop truth table, 0 0 means yes, it is no change condition. So my output remains as it is, it continues here. Since in the previous it was 0, now it continues to 0 once again, because it is 0 0 means no change condition. This is how at the edge, each edge of the clock transition, whatever the inputs are there, that is reflected at the output, no matter the input changes in between. So in between in the sense here, you can just see here before this next edge starts. So now the S has been flipped out to 0 and 1, but my output remains as it is. So this is nothing but we are talking about edge triggering SR flip flop, which triggers the output changes with respect to the positive edge of the clock. It can be even triggered for the negative edge of the clock also. So similarly, we discussed D flip flop in the previous session. So as you know what is D flip flop, so how it is formed. So we have discussed in the previous class, D flip flop is nothing but you are combining the input of S and R with an inverter. I am tying this S and R and I am making as a single input, that becomes D flip flop. So I am shorting this single input to S and R, that becomes D. So what is D flip flop? Once again, D flip flop is a data flip flop which transfers the data. Whenever my data, it can be an either 0 or 1. So with respect to the clock pulse, with respect to the clock edge, this input has been transferred to the output. So that is nothing but D flip flop. Edge trigger D flip flop, you can just see over here, my inputs are D and this is clock, and Q bar, Q complement is nothing but an output. Whenever my input is 0, so whenever the clock triggers at the positive edge, the D is transferred to the output side. So when my output Q is 0, we call this condition as reset condition. Similarly, whenever I give my input D as 1 with respect to the clock edge, then my output remains 1. So same thing is transferred at the output side. So we call this as set condition. So in D flip flop only we have reset and set condition. You can just see over here the timing diagram summarizes the operation of this positive edge trigger D flip flop. So this is the truth block diagram of D flip flop. So in the you can just see the input to D is, there is only one input, two outputs, and we have a clock here. So with respect to D, suppose it can be a 1 or a 0, any transition it can be D. So whenever your clock output is I, you can see this portion, green line represents clock. So this is my Q. Whenever the clock is I, the same D is transferred over here. You can just see here this portion. This portion represents Q following D when clock is I. When clock is low, so even though the D has changed, it remains constant, output remains constant, input is been latched. We say that the input has been latched. So whatever it has stopped at the previous, here you can see the previous was logic 1, that continue until the next clock becomes I. So when the next clock becomes I, same D is transferred at the output side. So when the clock is low, here the blue region represents clock low, so it never the D is transferred at the output side. So whatever the previous output, that will be latched here, stored in the flip flop. So similarly you can just see here D, then this is your D input, and this is clock. This is for negative edge triggering, this is for positive edge triggering. So that's why this complement has been written here. So your output follows input whenever your clock is low. So here whenever your clock is I, your output remains latched with the previous condition. So these two represents the timing diagram of edge trigger D flip flop with respect to positive clock and negative clock. This is, you mean to say that positive clock in the sense positive edge triggering, negative clock in the sense negative edge triggering. The flip flop can be either of this case. Based on the edge triggering, your output gets reflected. So now let us discuss what is JK flip flop and how it is designed and how it operates. So JK flip flop is a further extension of SR flip flop. As usual, it operates as SR flip flop. As we discussed in the previous session, SR inputs we treat this as SR NAND gate flip flop latch. When I put a clock for this, it becomes flip flop. So how to introduce clock for this? I introduce two AND gates. I connect these two AND gates and I represent this, give an additional signal called clock. So this is an SR latch. Top of it, if I add two AND gates with a clock, this becomes SR flip flop. So now how to convert this SR flip flop to JK? Why JK? So as we have discussed in the previous session, we have in SR flip flop, when S and R both are 0, no change condition, we have 0 and 1 set condition, 1 and 0 reset condition. So the last one, 1-1 operation was an invalid, indeterminate, forbidden condition. In order to overcome this unused condition, to make it into use, we redesign the flip flop and we name this as JK flip flop. In order to get back this 1-1 condition, which was there a drawback in SR flip flop, so we are going to get that condition here using some additional some minor changes in this flip flop. So this is SR flip flop. Now what I am going to do now, I convert this JK by connecting this is Q and this is complement of Q. So I connect this input to Q complement. So this will be treated as, now S has changed to J, here R I am changing it to K. So additional inputs are given here. So similarly here from this second gate I am connecting here back to Q. So this is an additional connection that we make in JK flip flop. So that is how we transform your SR flip flop into JK flip flop in order to overcome the last condition, that is forbidden condition. So you can just see here the feedback is here Q complement, for the lower gate it is Q. So now we will write the truth table of this JK flip flop. So J, K, Q, Q complement 0 0 0 1 1 0 1 1. As we know, we have 4 conditions here. So when J and 0, and here we have additional input called clock. So I write clock here. So whenever clock is I, so this arrow upwards represents clock I. Whenever there is a clock I, both the gates are enabled. So now I am giving input 0 0. As usual, if I give 0 0, 0 and 1, your AND gates are disabled here. Output of the both the AND gates are 0 0. So this is nothing but your SR latch. Input to SR latch, when both inputs are 0 to SR latch, you know it is a no change condition. So we get no change condition here. So let us switch over to the second, that is whenever I give 0 and 1 here, so upper gate is disabled, my output is 0 here, lower gate is enabled, so my output is 1 here. So now my input to SR latch is 0 and 1. So 0 and 1 combination to SR latch is nothing but 0 and 1 condition to SR latch is nothing but reset condition. So your flip flop is in reset condition. So this, note that this represents SR latch. So in top of it I am connecting an AND gate, AND gates to give clock. So only this feedback connection represents JK flip flop. Now coming to 1 0 condition. So if I give 1 here to the J, 0 to K, so this gate is disabled, this gate is enabled. So 1 and 0 input to SR latch is nothing but set condition. So what I will get here? Set condition. So it remains same. So as you see, the first 3 conditions are same as your SR flip flop. So why I am designing this JK flip flop then? Right, the last condition what we add in SR was forbidden or indeterminate condition. So now let us find how this going to override or how I am going to rectify this condition. So when I give both 1 and 1, so if my inputs to J and K both are 1 and 1, both the gates are enabled. So when both the gates are enabled, input to SR is 1 1. Assume that in the previous we add Q as 0 and Q complement as 1. So when Q is 0, 0, so you are giving 1 here, any of clock is 1. So when Q is 0 and Q complement is 1, you are assuming now here Q as 0, Q complement as 1. Now I am analyzing this gate. So Q as 0, K is 1, clock is 1. and here Q complement is 1, J is 1, clock is 1. So the lower gate is disabled. Since we have 1, 1 and 0, the lower gate is disabled. So upper gate is enabled. So what is going to happen now? So now this is 1 and 0. So 1 and 0, once again it is, your output will be 1 and 0. Similarly, so now this Q has become 1. So Q has become 1 in the sense, now this gate has changed to, input to this gate is 1. So Q complement, now it has become 0. So Q complement I will be giving as 0. So what is happening here? Now S has become 0, R has become 1. So 0 and 1 goes to reset condition. So you can see this pattern here, Q has changed from 0 to 1, 1 to 0. So similarly here, so this is continuing. You are getting a pattern. This pattern is nothing but flipping from 0 to 1, then 1 to 0 back. So this is continuing over here. Because of this feedback connection, your output keeps on changing. So from 0 to 1, 1 to 0. So this condition is called as toggle condition. Output switches from 0 to 1, 1 back to 0. So we have eliminated indeterminate forbidden condition in SR flip-flop. By introducing this feedback, we get a condition called toggle condition. You can just see the timing diagram of this JK flip-flop. So this is your clock, J input, K input. So when my J is 1, K is 0, at the clock edge, 1 and 0 condition is nothing but set condition. So my output is set to 1, that is Q becomes 1. So next, coming to the next clock edge, my J is 0, K is 1 over here, so it is reset condition. So now we have got the output as 0. Similarly, when I come to this position, next clock edge here, 0 and 1, same, it continues here. This clock edge, you can see J as well as K, both are 1. So what should be my output? Previously it was 0, now it is, previously it was 0, now it has changed to 1. So similarly, next clock cycle, we have both J and K 1. So if both J and K are 1, once again it is toggling. So you can see it is toggling from 0 to 1 and 1 to 0, switching or toggling from 0 to 1. This condition is toggle condition. So Q complement is reverse of this Q. So this is nothing but the JK flip-flop truth table and its timing diagram. So let us discuss one more concept about JK flip-flop, that is nothing but racing problem. So what is this race around condition? As I discussed, J and K both are 1, your output gets toggling continuously as long as your clock is I. So it continues toggling whenever the clock is I repeatedly. Practically it is not so, since clock pulse has got propagation delay more compared to this a single output delay. So I will show you an example. As I discussed, this is a clock. When my J input and K input is 1, your output toggles. Till where it toggles? Till the clock becomes low. So my Q output will be like this. Once again 0, because my clock is low, so it doesn't toggle. Next clock pulse, it toggles. So this is nothing but race around condition. So because this clock pulse, since clock pulse is more than the propagation delay, so within one clock pulse this propagation delay is more. Within one clock pulse it switches. Flip-flop propagation delay is less compared to the clock propagation delay. So it keeps on switching here, racing. We call this as racing. This race around condition is due to the feedback problem and the delay mismatch between the clock pulse and the flip flop. So how to avoid this race around condition? So there are three methods wherein I can avoid this race around condition. Either I should make this clock pulse propagation delay less than this flip flop, practically which is not possible. So since this is propagation delay and this is clock pulse, time period of this clock pulse, that is T on should be less than TPD. So what is this TPD? It is nothing but the delay of the flip flop, which is always in the order of nanoseconds or picoseconds, which is practically impossible to make this clock pulse lower than this. So this is a possible case we can do, but practically it is impossible. The second case, another way is by using edge triggering. So I can use edge triggering. So when I use edge triggering, your output should switch or toggle only at the transition of the next clock pulse, next edge, so that I can avoid this race around condition. Third is by using master slave flip flop. So what is this master slave flip flop, why it is designed and how it is designed, let us discuss next session. So before that, I will be discussing something related to timing, as we just discussed about the propagation delay and delay of the clock and as well as the propagation delay of the flip flop. So what exactly is what do you mean by timing? So timing is nothing but switching time. Switching time of a transistor, as you know, the flip flops are once again made up of gates. So gates are in turn made up of transistors. So this transistor has got switching time. So switching time is nothing but changing its pattern from 0 to 1, on to off, off to on. So this is nothing but switching time. So there are two concepts we are discussing over this timing, that is nothing but setup time and hold time. So whenever I give a data, assume that this is a data you are sending. So whenever I am giving a data, then of course we give a clock as a control input to send your data. You can just see here, this is clock edge. So and this is data. This data remains I in this interval. Before this clock edge and after this clock edge, we discuss something called timing. So this is called as T setup. We call this as T setup, and this we call it as T hold. What is this T setup time? T setup is nothing but setup time is the interval before the clock where the data must be held stable. So before the clock the data must be held stable. So you should hold this data. So this is nothing but setup time. So what is hold time? Hold time is the interval after the clock, after this clock, where your data must be held stable. So the data has to be held long enough for the interval so that the transistor should switch states. The transition is assured. We can allow data bit to change. So hold time and setup time are very much important in order to hold your data. So hold time, I can also define this hold time as the minimum amount of time that the data bit must be present after the positive transition of the clock. So this is nothing but setup time and hold time. So it all depends on switching time of the transistors. So as I discussed about race around condition, how to eliminate this race around condition, we use a concept called JK master slave flip flop. What exactly is this? It is the same JK flip flop, but it is connected. Two JK flip flops are cascaded So flip flop 1 and flip flop 2 are joined or cascaded 2 stages. The first stage is called as master, the second stage is called as slave. So how exactly this works? So now let us discuss the operation and the circuit, how to write the circuit diagram for JK master slave flip flop. So as you know, we have used NAND gates, so this is JK flip flop with one more stage I will be writing here. So what I am trying to do here, I have clock, I have J, I have K, and of course for JK flip flop I need a feedback connection. So what I am doing here, this is one flip flop, first flip flop, this is second flip flop, we call this as master, we call this as slave. So what exactly, how it exactly differs from a normal JK flip flop? In normal JK flip flop, I have connected, I have taken an additional input both from J and K and I fed back to this Q and Q complement. So here instead of doing this connection in first stage, I am going to do this connection in the next stage. So I am connecting here. So similarly, I am connecting K here. So instead of connecting earlier what we discussed, feedback connection over here, I have connected to the second stage. So what I should do here, I should join first stage to second stage. So output of the master, I treat this as QM complement is connected as an input to the slave. So what about this clock? So how to connect clock? So I give positive clock to the master and I use an inverter to connect to the slave. So master and slave are separated by a clock. So positive clock to the master, negative clock to the slave. So the feedback connection is given at the end. So by doing this, how exactly we are going to minimize or eliminate raise around condition, let us discuss. So we will write the truth table of this, how exactly it works. As usual, we know I give this name as slave clock. So when clock is high, when clock is low, what is the output of the master and what is the output of the slave? So as usual, whenever the clock is high, the first flip flop operates normally. When I give 0 0, it is no change condition, and when I give 0 1, it is reset condition, set condition. So this is toggle condition. So whenever the clock is high, here the clock is low to the input to the slave flip flop. So whenever the clock is high, the normal operation takes place in the first stage. What happens to the second stage? Since clock is low, the gates are disabled here. So the input to the slave is nothing but output of the master. So now slave doesn't respond, remain as it is, no change. When I make clock low, then the master will be in no change condition, doesn't operate, only the slave responds. When the clock is 0 here, the inverter becomes, output of the inverter is 1. So now the slave is triggered, the second stage flip flop operates. Whatever the previous state that has been stored, that will be transferred at the output side. So based on the outputs coming from the first stage are acting as a input to the second stage. When a negative clock is given, so first stage is disabled, second stage is enabled. So slave follows the master, so it just transmits whatever the output coming from here, that is reflected at the output side. The slave is driven by the outputs of the master, which is in accordance with the input given from the master. So slave follows the master. So that's why we call it as master slave flip flop. So master is active when it is during positive edge of the clock, due to which your output changes. In turn, the slave is active in negative edge where it follows the previous stored output of the master. So now slave is active, which transfers the data. Positive edge, master is active, slave is inactive. Negative edge, slave is active, master is inactive. So at a time, one of this flip flop is active, the other is inactive. So based on the output of the master, the slave transfers to the output. So this is nothing but JK master slave flip flop. So slave decides its output depending on the inputs of the master during the negative edge of the clock. So there is another flip flop that we have not discussed so far, that is toggle flip flop. So we discussed this toggle flip flop only once we know about JK flip flop. So toggle flip flop is nothing but, in JK flip flop we have 4 conditions, as you know: no change, set, reset and toggle. Suppose for some applications I want only toggling, I don't want set and reset conditions, then I transform this JK flip flop to toggle flip flop. It is nothing but J and K are tied. If this becomes input as T, so if my T is 1, both inputs are 1 and 1. To the JK inputs 1 and 1 means it is nothing but toggling condition, it goes in toggle state. So that's why we call it as T flip flop. T flip flop is nothing but tying J and K together, shorted and making as a single input, that is T input. So output is Q and Q complement, so which remains toggling based on the input given. So now let us discuss switch contact bounce circuit. So what exactly is this switch contact bounce circuit? So in digital systems we use mechanical switches for conveying an electrical signal. So whenever I need to send some data, I press the switch. The switch used on the keyboard, it can be used on the keyboard or at computer, or a toggle switches or a push button. So I press or I release, either I can make it on or off, so by pressing the particular switch. So what exactly happens with the internal operation of the switch, how exactly it operates? You can just see here, switch is represented by the symbol and we give voltage here, and this point is called as A. So when the switch is open, there is no connection here, it is nothing but it is directly connected to the ground, so no voltage appears here, it is 0. Whenever I close the switch or I press the button, there exits a path, so where you get a power supply or a connection, So it will be treated as logic 1. So there is a concept called contact debounce in case of mechanical switches. So whenever I press a key, so the switch debounces multiple times in order to come back into normal position. So when a contact is closed or opened, so we call it as make or break. So it takes many times finally to settle down to stable state. So this is nothing but contact debouncing is a process of debouncing is nothing but a process of removing these bounces. So whenever I press a switch, so it bounces from 0 to 1, 0 to 1, finally it will settle down. So in order to remove this bouncing, we call it as debouncing. So when a contact is closed or open, I call it as switch closed or open, make or break, so many times before settling it into new state. So see this waveform over here, you can see an input signal suffering from contact bouncing. So whenever a switch is in contact or connected, then we call it as logic 1. So whenever I release or break the circuit, then we call it as logic 0, switch goes to 0 state. So while returning from 0 to 1, so while moving from 0 to 1, it takes much transition to reach this 1. So whenever your switch is in off condition, when I press the button, so it has to move from 0 to I state, low to I state. So by moving in between, it bounces many times and then comes for a stable condition. Similarly, when I want to go from I to low state, it bounces many a time and then it goes to a stable state. So this is nothing but contact debounce problem. So this is the major problem in digital circuits whenever we are contacting the digital circuits with the mechanical switches. So this happens to settle down. We will represent various representation of flip-flop. We can represent this flip-flop in various methods. For example, I will represent the flip-flop in terms of truth table, characteristic table, excitation table. From that I am going to generate characteristic equation. Then I can develop finite state machines. Now let us discuss how we will write the truth table, characteristic table and then excitation table of all the flip-flops. So we will now start with, we have already discussed truth table of various flip-flop. So we will write truth table of SR flip-flop. S and R, we add outputs Q n plus 1, 0 0 0 1, we have 4 combinations here, since 2 inputs 4 combination. So no change condition. Here we add reset condition, set condition, indeterminate condition. Either I can write this as X or question mark. So this was SR truth table. Now I am going to write characteristic table for this. So what is characteristic table? So characteristics table is nothing but I consider the present state, then inputs, then I am considering what should be my next state. So I consider the present as well as the inputs, present output, inputs, then the next state output. So we have 4 combinations as usual. Since we have 3 inputs, I have to take up, now I have to consider Qn as also an input. The functionality of the characteristic table is nothing but it is with respect to 3 inputs, S and R and the present output. So 1, 2, we will be writing all 8 combinations here. Now let us see. So what is my next state? What should be my output? So whenever it is 0 0 condition, so it is no change. It was whatever is the previous, the same thing is retained. As usual, you know, 0 1 and 1 0, it is reset set condition. This is indeterminate. So now my next state has become 1. The present state is 1. 0 0 means no change condition. My next state will also be the same as the present state. So it is 0 1 reset condition, set condition, indeterminate condition. So this is nothing but characteristics table. From this characteristic table, I can get an equation for the next state. How to get the equation for next state? So I am going to draw a K map, 3 variable K map. From 3 variable K map, so I represent inputs as S and R and the present output. So the present, these are the combination I am using it. So I am going to fill this. I am going to fill this question mark as don't care. So now 0 and 0, 1 and don't care, 1 and 0, 1 and don't care. So I am going to group this and this. So I will get equation now Qn plus 1 is equal to, so if I take up this is S is common, R is changing, so I will consider only S. Here if I take up this 2, so Qn S or Qn, and which is common over here, so I have taken S here, so here it is common S, and I am grouping these two corners here Qn, and I need to take the common here, it as R. So R complement. This equation generated from characteristic table is called as characteristic equation. What does this characteristic equation say? It represents the next state in terms of the inputs as well the present output. So the next state in with respect to the present state and the inputs will give you the characteristic equation from this characteristic table. So next is excitation table. So I am going to draw an excitation table. This is with respect to present state, next state, and now I am going to decide based on present state and next state. I am going to design what should be my inputs. So since we have 2 combinations, I will be generating 2 inputs, 4 combinations. As you know, 0 0 and SR will represent in terms of Qn and Qn plus 1. Now check this characteristic table. So whenever Qn and Qn plus 1 are 0 0, so 0 0, so both the conditions you should see, Qn plus 1 and Qn and Qn plus both are 0. So what is my S and R? In this my S is common, it is constant 0, but R is changing. So I write that S is remaining constant, R is changing. R could be either 0 or R could be 1. So similarly the next condition I should see Qn as 0, Qn plus 1 as 1. So Qn as 0 and Qn plus 1 as 1. 1, 0 and 1, 0 and 1. So since I don't know about this, either it can be it's an indeterminate condition, so I consider Qn 0, and 1, 0 and 1. So, what is my inputs? So, here it is 1 and this is changing. So, now 1 and 0. So, 1 and 0 combination here 1 and 0. So, 1 and 0. So, I am going to see once again here 1 and 0 this indeterminate condition. So, S is changing, R is 1. So, last condition 1 and 1 condition, I am considering this 1 condition. So, in this 1 and condition, so S as well as R both are changing. So, since I am giving this 1 as forbidden condition, so I will be unable to predict here. So, this is what I am going to write an excitation table from the characteristic table. Characteristic table is generated from the truth table. So, finally, this excitation table is useful for constructing or converting the flip-flops, right, as well as designing counters. So, basically designing counters we use JK flip-flop. Similarly, we can generate same thing for all flip-flops SR, JK, D and T. So, you can see here the characteristic equations generated from SR flip-flop. So, same thing D flip-flop, the present and next state. I am giving the conditions here D 0 0 and 1 1, D and Qn, then I make 4 combinations out of it. Since Q follows D, so whenever the D is 0, Q is 0, D is 1, Q is 1. So, I am going to represent D and Qn as an input to a K map. So, I get an equation for Qn plus 1, that is nothing but D. Characteristic equations similarly I can generate for JK flip-flop by giving JK, Qn and Qn plus 1. So, entering this Qn plus 1 and Qn, we will get 2 equations, Qn plus 1 in terms of J and Q, J and present state plus K and present state. Similarly, characteristic equations of T flip-flop we can generate. So, flip-flop excitation table specifies the next state when the input and the present state are known. During the designs of sequential circuit, the required transition from present state to the next state, we need to find out the flip-flop input conditions that will cause the required transition. For this reason, we need this table that lists the combination, input combinations for a given change of state. Such a flip-flop is, such a table is called flip-flop excitation table. So, as we discussed, excitation table of SR flip-flop, similarly excitation table of D flip-flop, JK flip-flop. So, we are going to generate 0 and don't care, 1 and don't care. This don't care may be either 0 or 1. So, finally, I conclude this session by making you to understand the truth table, excitation table of flip-flops for edge triggering, and we have discussed the cause of contact bounces and to describe the solution for this problem. Learn how to write the characteristic equations of these flip-flops.